46 years ago, Mount St. Helens killed 57 people in the worst volcanic disaster in modern North American history. This week, the same mountain is shaking again. A swarm of small earthquakes has been registering directly beneath its crater, paired with a second signal that seems to make no physical sense, a surface that is quietly sinking instead of rising. It has scientists watching this volcano with the exact same precision they brought to the spring of 1980. In the next few minutes, you will learn what that deep shaking actually is, and how geologists tell the difference between routine maintenance and a real countdown. On Thursday morning, a cluster of micro-earthquakes registered beneath Mount St. Helens, the most dangerous active volcano in the Pacific Northwest. The monitoring networks that watch the mountain around the clock, Natural Resources Canada through the Canadian Hazards Information Service alongside the United States Geological Survey, formally located only a handful of them. One came in at magnitude 0.9 near 8:21 in the morning. Another registered at magnitude 0.8 about an hour later. On paper, that is almost nothing. Quakes that small are not felt on the ground, not heard by human ears, and not remarkable for a living mountain. But here is the physical reality that stops you in your tracks. That swarm arrived while the mountain was doing the exact opposite of what your instincts tell you a waking volcano should do. Mount St. Helens is not bulging, it is not swelling outward. Its surface, measured continuously by satellite radar and high-precision geodetic receivers, has been settling downward for years, steadily sinking. The intuitive picture, the dramatic headline version everybody carries in their head, says earthquakes plus a rising volcano equals magma climbing toward the crater. What St. Helens is actually showing us is earthquakes plus a surface that is quietly sagging. A mountain that is shaking while it settles. Let me be completely clear about the immediate stakes before anyone panics. As of this weekend, Mount St. Helens sits at Volcano Alert Level Normal, Aviation Code Green. There is no eruption warning. No official agency is forecasting one. This is not a mountain about to blow, but it is also very far from nothing. And the reason it is not nothing is the core mechanics of what follows. A volcano can be intensely alive, actively rebuilding its magmatic plumbing miles below the surface, and still stand years or decades away from an eruption. The question underneath this swarm is the one that actually matters, and it is far more unsettling than any single isolated tremor. If St. Helens is quietly refilling beneath a sinking surface, how does anyone know when the quiet turns into a real countdown, and are we even watching the right signals? To understand why a tiny swarm matters, you have to follow the plumbing straight down. Mount St. Helens is not a simple underground bucket of lava waiting to spill over. It is the surface expression of a continuous crustal system reaching 16 kilometers into the Earth. Down at that deep boundary, magma forms and begins its agonizingly slow climb upward. It collects in a primary storage reservoir roughly 4 to 10 kilometers beneath sea level. That deep reservoir is the mountain's engine room, and it is the key to everything happening today. When that deep system takes on new material, when it recharges, the reservoir presses outward on the surrounding rock. That immense hydraulic pressure forces fluids through microcracks, stressing the rigid crust. And stressed, cracking rock does exactly one thing: it produces tiny earthquakes. This is what geophysicists call a recharge swarm. The name tells you precisely what the phenomenon is. It is not the sound of magma breaking for the surface. It is the acoustic signature of a reservoir refilling miles down, pushing gently on the solid rock that pens it in. The earthquakes are a symptom of the mountain feeding, not the mountain erupting. It helps to sit with just how small these events actually are. The seismic magnitude scale is not a ruler. It is a steep set of stairs, where every full step down represents a 32-fold drop in energy. A magnitude 0.9 is not a slightly weaker version of a quake you would feel standing in a room. It is thousands of times fainter, an event that exists only as a subtle squiggle on a hypersensitive broadband seismograph. You could stand at the exact spot on the mountain directly above one of these tremors and feel absolutely nothing. That is the true scale of what we are analyzing. Dozens of deep whispers from a reservoir miles down, not a single sharp crack from magma reaching the top. That distinction is the entire difference between a routine geological week and a national emergency, and it hangs entirely on where the quakes sit in space and what the ground above them is doing. Which brings us to the most misunderstood detail in this entire story: the gap between what official catalogs list and what independent observers see on raw traces. There is a discrepancy at the center of this event, and it is entirely real. While monitoring networks formally located only a few events on Thursday morning, observers reading raw seismograph feeds argued the true count was far higher, potentially dozens of discrete micro-events across a single 24-hour window. So which is it, a handful or dozens? The honest scientific answer is both. Understanding why is how you clear away the conspiracy claims that inevitably follow. A narrative circulates every time this happens, that monitoring agencies are suppressing data, hiding the true extent of the shaking. It sounds compelling because raw traces do show more wiggles than the public catalog listings. But that gap is not suppression, it is standard physical processing. For an earthquake to be formally located with latitude, longitude, and depth, the exact same signal must be recorded cleanly at multiple independent stations. A micro-event too faint to clear the noise floor at more than one instrument cannot be placed in space within tight error bounds. Force those unlocatable whispers into the official catalog, and you do not get better science, you get corrupt data. The network openly acknowledges that many tiny events occur below the detection threshold. The catalog is not a ceiling that hides the truth, it is a floor that openly defines certainty. If this week's activity feels unprecedented, it is worth remembering that St. Helens executed this exact sequence 10 years ago, and nothing catastrophic followed. In the spring of 2016, the mountain produced an identical recharge swarm, generating over 130 formally located quakes across 8 weeks alongside hundreds of unlocated whispers. The USGS and regional monitoring partners noted no shallowing, no gas spikes, and no ground inflation. What they were watching was patient underground recharge, the exact same process that historically ran for 17 straight years between 1987 and 2004, before a gentle, dome-building extrusion began. The mountain refilled quietly for nearly 2 decades before doing anything at the surface, proving that deep recharge operates on a timescale measured in years and decades, not hours and days. So what actually answers the central question of this episode? How do we know when quiet recharge turns into an active, irreversible countdown? The answer lies in 5 specific, unmistakable physical shifts that no monitoring network could ever miss. A upward migration of earthquake focal depths tracing magma on the move. The sudden appearance of sustained harmonic volcanic tremor. A hard reversal from surface sinking to aggressive ground inflation. A massive surge in emitted sulfur dioxide gas, and phreatic steam explosions clearing the upper vent. Until those 5 signatures align simultaneously, the mountain is not preparing to blow. It is simply performing the slow, quiet, mandatory maintenance of a living continental machine. A single broadband seismometer array sitting on the cold flank of Mount Meager in British Columbia recorded over 700 distinct micro-events in late 2007, and not one of them was felt by a human being standing 500 meters away. That silent record established the baseline for volcanic monitoring along the Canadian Pacific Rim. A volcano can execute thousands of structural adjustments deep in the crust without ever breaking the silence on the surface. To measure the true significance of what is happening at Mount St. Helens today, you have to measure it against the strict historical baseline carved into the North American continent over the last 4 decades. Before the spring of 1980, the mountain had slept in near total silence for 123 consecutive years, a period of apparent dormancy that allowed dense evergreen forests to climb high up its flanks and led surrounding communities to treat the peak as a permanent, unchanging fixture of the Cascade Arc. That illusion shattered permanently on March 16, 1980, when a series of microscopic seismic signals began registering on the regional network maintained by geophysicists in the Pacific Northwest. What followed was not a sudden explosion, but a grinding 2-month structural breakdown that rewritten how Earth scientists quantify volcanic hazards across the entire Pacific margin. By late March 1980, the baseline had shifted from near-zero background noise to hundreds of daily earthquakes, culminating in a continuous seismic hum that signaled magma actively forcing its way into the upper edifice. On 27 March, a small phreatic steam explosion blasted a 75-meter-wide crater through the ice cap at the summit, sending an ash plume 4 kilometers into the atmosphere. Over the next 7 weeks, the mountain did something that had never been documented with modern geodetic instruments on the continent. The entire northern flank began to deform outward at a rate of up to 1.5 meters per day. As pressurized dacite magma intruded into the shallow system, it created a massive cryptodome, a swollen, unstable wedge of rock that eventually displaced the northern slope by more than 135 meters outward. The scale of that deformation was staggering. The displaced mass equaled roughly 1.5 cubic kilometers of rock, a structural overload equivalent to stacking 3,000 CN towers side by side along the mountain's edge. On the morning of May 18, 1980, at precisely 8:32 a.m. local time, a magnitude 5.1 earthquake struck directly beneath the peak at a depth of less than 2 kilometers. That single shock unseated the hyper-pressurized northern flank, triggering the largest terrestrial landslide in recorded human history. In a matter of seconds, 2.5 cubic kilometers of rock tore free and plunged down the valley at speeds exceeding 250 kilometers per hour, burying 40 kilometers of the Toutle River Valley under an avalanche of debris up to 180 meters deep. With the physical cap removed, the superheated hydrothermal and magmatic system instantly flashed into steam, releasing a lateral blast that accelerated across the landscape at 1,000 kilometers per hour. The thermal and pressure waves scorched and flattened 600 square kilometers of old-growth forest in a 180-degree arc, stripping mature trees from the earth like matchsticks across a distance equal to the entire urban footprint of Greater Vancouver. The vertical column that followed punched ash 24 kilometers straight into the stratosphere, darkening the sky across western Canada and depositing recognizable ash layers as far east as Edmonton and Calgary. The explosion permanently lowered the summit elevation by 400 meters, removing the top portion of the peak and leaving behind a horseshoe-shaped crater 2 kilometers wide. 57 people lost their lives that morning, including field volcanologists who were standing at observation stations 6 kilometers away, locations previously categorized as completely safe. That catastrophe forced a total rebuild of how North American scientific bodies, from Natural Resources Canada and the Geological Survey of Canada to their American counterparts, monitor active subduction zone volcanoes. In the decades since 1980, every single tremor, gas plume, and millimeter of ground displacement recorded along the Garibaldi volcanic belt and the Cascade Arc has been evaluated against that exact 2-month countdown. The historical baseline shows that a genuine, catastrophic reawakening is defined by 3 uncompromising parameters: rapid shallowing of earthquake hypocenters, extreme high-rate ground inflation exceeding meters per day, and massive continuous degassing of sulfur dioxide. That is the historical yardstick. When we evaluate the current microswarm against that precise 1980 baseline, the contrast is absolute. The current events are locked at depths between 4 and 10 kilometers. The ground surface is actively deflating downward due to cooling shallow lava domes, and gas emissions remain strictly within background parameters. To determine whether this baseline holds, viewers should watch for 3 explicit indicators over the next month. Any official reclassification of the volcano alert level by monitoring agencies, a sudden migration of focal depths above the 2-kilometer mark, or a net reversal in satellite-measured ground displacement from subsidence to positive inflation. A single GPS receiver bolted to a concrete pillar inside the crater of Mount St. Helens registered a vertical change of -2 centimeters per day during the late stages of the mountain's last active lava extrusion cycle, and that single reading contains the key to resolving the entire paradox of this week's shaking. The internet headline framing suggests that a volcano shaking while sinking represents a terrifying system failure, a signs-defying anomaly that old geophysics models cannot explain. But here is the critical correction move that sharpens the entire story. The surface sinking is not a contradiction of deep magmatic activity. It is the physical proof that two completely different layers of the mountain's internal engine are operating independently at the exact same time. The upper skin is cooling and shrinking, while the deep engine room miles below is recharging. The physical mechanism that governs this split behavior is known as vertical decoupling, and understanding how it works step by step reveals exactly what is breaking inside the mountain and what remains completely structurally intact. To see the process clearly, you have to picture the volcano as a two-tiered hydraulic system, reaching from the upper mantle down through 16 kilometers of continental crust. At the absolute bottom of this system, deep beneath sea level, fresh basaltic melt continuously ascends from the subduction zone and collects in a primary magma reservoir sitting between 4 and 10 kilometers beneath the crater floor. As new magma enters this lower chamber from below, it builds immense pore pressure within the surrounding country rock. This hydraulic pressurization forces volatile-rich fluids into microfractures, increasing stress across regional fault plains and causing rigid crystalline rock to snap. That microfracturing is the physical source of the earthquakes currently registering on monitoring networks. It is the acoustic sound of a deep storage tank against its rock walls. Now step up to the shallow system, the upper 2 kilometers directly beneath the crater. During the volcano's last active eruption cycle, between 2004 and 2008, it extruded over 90 million cubic meters of dense, pasty dacite lava into the crater floor, building a massive solid dome and a series of towering rock spines. That fresh volcanic material was emplaced at temperatures exceeding 800 degrees Celsius. Over the subsequent 16 years, that shallow rock mass has been executing a continuous thermal contraction. As the hot dacite slowly cools, degassing its remaining volatile compounds and crystallizing into solid mineral structures, it physically shrinks. At the same time, the colossal mass of the new lava dome, weighing hundreds of millions of tons, is physically crushing the weak, hydrothermally altered rock directly beneath it, causing the crater floor to sag downward under its own immense weight. This shallow thermal contraction and gravitational settlement pull the surface downward at a rate of several millimeters to centimeters per year. The deep reservoir miles below is inflating, but the signal of that inflation is masked at the surface by the sheer magnitude of the shallow cooling and sagging. The two zones are decoupled. The bottom is filling, the top is sagging, and the micro-earthquakes are the acoustic bridge between them. Geophysicists at Natural Resources Canada, the Canadian Hazards Information Service, and partner observatories track this exact mechanical breakdown using an array of hyper-precise instruments. Borehole tilt meters installed in bedrock detect angular changes in ground slope down to fractions of a microradiometer. Continuous GPS arrays measure precise three-dimensional positions every 30 seconds, tracking surface movement down to individual millimeters. Meanwhile, broadband seismometers operated across the Cascade chain filter out background cultural noise, ice quakes from glaciers, and landslide rumbles to isolate the precise high-frequency crack of rock fracturing at 4 kilometers depth. The evidence confirms that the deep plumbing is taking on new fluid, but the structural cap remains utterly locked and undisturbed. The old simplified model that assumed a volcano must swell like a balloon before every minor seismic event has been replaced by this multi-tier mechanical consensus. The mountain is executing routine structural maintenance, refilling its primary battery while its shallow roof cools. To verify whether this multi-tier mechanics holds or breaks down into a true structural emergency over the coming weeks, watch 3 precise physical metrics. First, whether deep microseismicity begins migrating upward into the shallow 2-kilometer zone. Second, whether borehole tilt meters detect a sharp, positive inflation curve that overrides the shallow subsidence signal. And third, whether differential satellite radar interferometry shows localized bulging along the crater walls. Until those physical metrics shift, the mechanical baseline remains absolute. Mount St. Helens is not preparing an explosive blast, but quietly refilling its deep structural reservoir miles beneath the forest floor. 3 separate automated warning systems across Western Canada and the Pacific Northwest registered simultaneous pressure, seismic, and atmospheric anomalies within a 48-hour window in September 2025, and every single one of them traced back to a single mountain. To understand why a micro-swarm beneath Mount St. Helens creates immediate real-world ripples across Canadian infrastructure, you have to trace how a volcanic event scales up from microscopic shaking to continental impact. The media headline version suggests that a quiet micro-swarm is an isolated event in the wilderness with 0 real-world consequences until an actual explosion occurs. But here is the critical correction move that sharpens the entire picture. A living volcano does not need to erupt to disrupt human systems. The mere potential for reawakening forces immediate, high-stakes operational adjustments to transboundary airspace, regional hydroelectric grids, commercial shipping corridors, and civil defense networks from Vancouver to Calgary. The mechanism of real-world impact begins in the air. When Mount St. Helens threw up massive dust plumes in September 2025, it was not new magma breaking the surface, but high winds lifting 45-year-old ash deposited during the 1980 eruption. Yet the atmospheric response was immediate. Microscopic volcanic ash, composed of razor-sharp glass shards and pulverized rock, is airborne poison for jet engines. When ingested into a turbine operating at 1,400 degrees Celsius, glass ash instantly melts, coating the internal turbine blades in liquid glass, choking airflow and causing catastrophic engine flameout. That is why NAV Canada, working in direct coordination with the Canadian Hurricane Centre and the Canadian Aviation Weather Centre, maintains strict operational protocols for transboundary airspace along the Pacific Corridor. A major ash column rising 10 kilometers into the atmosphere over the Cascades does not respect international borders. Prevailing upper-level jet streams carry ash plumes directly northeast across British Columbia and Alberta within 3 to 6 hours. A single major explosive event would immediately ground transboundary commercial air traffic, severing flight paths between Vancouver, Calgary, Seattle, and Toronto, impacting over 100,000 passengers daily and costing the regional economy tens of millions of dollars per hour in delayed logistics. Ground infrastructure faces an equally complex mechanical threat. Take the vast hydroelectric networks managed by BC Hydro and regional utilities. Mount St. Helens sits within the Columbia River Basin, a massive transboundary hydrological system that feeds shared hydroelectric capacity across the Pacific Northwest. In 1980, catastrophic lahars, volcanic mudflows with the consistency of wet concrete, swept down river valleys at 50 kilometers per hour, carrying 35 million cubic meters of debris into downstream channels. A lahar is created when superheated volcanic ash instantly melts glaciers and snowpacks, blending water, mud, trees, and boulders into a dense fluid that scours riverbeds to bedrock. If a major thermal event were to mobilize the glacier currently growing inside the crater of St. Helens, the resulting lahars would choke river networks, clogging intake structures, disrupting municipal water supplies, and forcing emergency shutdowns of regional power plants. The scale translation is staggering. A medium-sized lahar carries enough sediment to fill Vancouver's BC Place Stadium over 20 times in a single afternoon. For residents living in lower mainland British Columbia and southern Alberta, the daily reality of living in the shadow of the Cascadia subduction zone and its volcanic arc is governed by Public Safety Canada and the National Alert Ready System. The seismic networks maintained by Natural Resources Canada through the Canadian Hazards Information Service work continuously to differentiate routine tectonic tremors from magmatic acceleration. When an active volcano begins shifting from recharge to countdown, emergency management agencies must execute immediate real-world closures, severing mountain rail corridors that transport millions of tons of grain and potash to the Port of Vancouver, shutting down trans-provincial highways and establishing exclusion zones. Even in a state of quiet background recharge, the economic toll of monitoring, infrastructure hardening, and emergency preparedness along the Cascadia Arc is measured in hundreds of millions of Canadian dollars annually. To track how this real-world impact evolves over the coming weeks, viewers should watch 3 explicit operational indicators. First, whether NAV Canada issues formal aviation hazard advisories for regional jet routes over southern British Columbia. Second, whether Emergency Management BC updates regional volcanic contingency plans for transboundary watersheds. And third, whether Ocean Networks Canada detects corresponding subduction tremor activity off the coast of Vancouver Island. Until those real-world warnings trigger, the daily situation remains completely stable. The mountain's quiet internal refilling is being watched continuously by the most sophisticated hazard monitoring network in North American history. On 26th of January 1700, at approximately 9 p.m. local time, the Cascadia subduction zone off Vancouver Island ruptured along a 1,000-kilometer front, producing a magnitude 9.0 megathrust earthquake that altered coastal geography in seconds and sent a massive tsunami across the Pacific Ocean. For over 326 years, that underlying tectonic engine has sat in near-total silence, quietly storing massive strain along the subduction boundary, while volcanoes like Mount St. Helens perform periodic structural adjustments high above the plate interface. The sensational headlines framing this week's events suggest that we are watching an imminent cataclysm unravel in real time. But here is the critical correction move that brings complete scientific clarity to the climax of this story. What is happening beneath Mount St. Helens is not a sudden, unheralded crisis. It is the physical proof of a continental subduction engine operating exactly as geophysics models dictate over multi-decade cycles. The honest boundary between what is established and what remains unresolved is precisely where scientific credibility lives. What is established beyond doubt by hypersensitive broadband seismometers, continuous GPS networks, and differential satellite radar interferometry is that a deep magmatic recharge is occurring between 4 and 10 kilometers beneath the crater floor. The reservoir is repressurizing as new material ascends from the mantle wedge, producing microseismicity as rock fractures under stress. At the exact same time, the shallow dacite dome extruded between 2004 and 2008 is executing a predictable process of thermal cooling, degassing, and gravitational consolidation, causing the surface to sag downward. The deflation of the top skin and the deep pressurization of the bottom reservoir are decoupled, 2 distinct phases of one living system. What remains genuinely unresolved is the exact time frame over which this underground recharge will continue before triggering a surface event. As demonstrated by the 17-year recharge interval between 1987 and 2004, a volcano can absorb deep pulse after deep pulse of fresh magma for decades without ever breaking its shallow seal. Or it can execute a sudden, rapid acceleration in shallow seismicity that shifts the system from background recharge to active eruption within weeks. Science cannot provide a magic calendar date for that transition, but it provides something far better, an uncompromising physical watch list that tells us precisely when the situation changes. Here is your checkable watch list to track over the coming weeks and months. First, monitor the spatial distribution and hypocentral depth of the seismic swarms recorded by Natural Resources Canada, the Canadian Hazards Information Service, and regional monitoring observatories. If focal depths remain locked 4 to 10 kilometers down, the process remains deep recharge. If those quakes rapidly migrate upward into the upper 2 kilometers directly beneath the crater, the countdown has shifted. Second, watch the geodetic data from continuous GPS stations. If the current surface subsidence flattens out and reverses into rapid, positive ground inflation exceeding centimeters per day, pressurized magma is actively pushing into the shallow edifice. Third, watch for formal advisory updates from emergency management authorities reclassifying the volcano alert level from normal to advisory or watch. Until one of those 3 checkable thresholds is crossed, the reality is plain and steady. Mount St. Helens is not counting down to an explosive disaster this week. It is executing routine underground maintenance within an active subduction zone. The mountain is simply doing what living volcanoes do between major historical chapters, cooling on top while quietly refilling miles down. Tell us in the comments below where you are watching this report from across Canada or around the world. Subscribe to stay informed as we continue tracking the real-world mechanics behind the continent's most critical geological systems.